Okay, here we go. Here's my first question to you. Let's say I want you to calculate for me. We're going to say we're going to adopt our normal convention. So I'm going to do motion on a line here, right? So I'm walking along the x-axis. What's the positive convention for motion on the x-axis? Yeah. To the right. Okay. Good. So I want to know then. I want you to please tell me what is my. I want you to calculate my average velocity. If I start, let's say 0 is right here. I'm going to start at 0, and I'm going to walk this way 3 meters, and I'm going to walk back this way a total of 5 meters, so I end up at -2, and I do that in 2 seconds.
-1. Oh,
well, that was fast.
What's the units?
Okay, what would they be?
-1 meters over second.
Good. -1 meter per second. Very good. Now, why the negative? Okay, because my average velocity took me from here to here, so my average velocity was moving in that direction, right? Okay, what was my average speed?
2 seconds.
What was my average speed? Once again, I went from
4 meters per second.
Total distance.
out 3, back 5 in 2 seconds.
4 meters per second.
4 meters per second. Agreed?
Yes.
Okay, good. All right, so on to acceleration. Now, let's review. Well, actually, before we do that, let's do just a quick review of the kinematic quantities we talked about. So we talked about let's make a list and break it into vectors and scalars, right? So I'm going to write them down, and you can define them out loud, but I'll just write them down. Right? I know, but don't peek at your notes. We're going to see how much we remember. Okay, so I want to know what's
Do scalars first.
okay, scalars. Okay, now let's limit ourselves to the kinematic quantities, the motion quantities that we talked about yesterday. What's an example of a scalar quantity? Speed. Okay. Okay, now without looking at your notes, some brave volunteer, tell me what is the definition of average, and really we talk about average speed, right? What's the definition of average speed? Average speed, yes, States.
Isn't it distance over time?
Yeah, total distance over time. Is this a possible answer? If I, could I have an average speed of 10 miles per hour? Could I have an average speed of 0.01 centimeters per decade?
Yes.
I could. It's pretty slow. Could I have an average speed of -3 meters per second? No, what's wrong with that?
That's not realistic.
Can't be negative, right? Speed is an inherently positive quantity, okay? What else? Distance. Good. Distance also is an inherently positive quantity. If I asked Delaney how far you went shooting for running, how far did you run? It wouldn't make sense for her to say, oh, I went out and ran -7 miles. What would that mean? Ran backwards? I don't know. Yeah. That doesn't make sense, does it? That's a positive quantity. Okay. What else? Time. Okay. And then along with time, I mean, this is kind of hokey, but what else? What other possible quantity might we refer to? Like, what would we call delta T? Difference in time, elapsed time. There we go. We could also talk about maybe elapsed time. Change in time being elapsed time. Okay. I think we got them all.
No, wait.
Okay, right. But the kinematic quantities. Was there anything else? Okay, but that's not a kinematic quantity. We threw it out as an example. But if we're just talking about motion, these are our motion quantities. Well, but once again, temperature and mass, and I think Paige, I threw out some other examples, but as far as motion is concerned, that's it. All right. Okay, vectors. Somebody give me a vector here.
Velocity.
Velocity, okay. And we're going to specifically.
Are you looking at your?
Okay, what about? Okay, so what's the definition of velocity?
Difference in change in.
Okay, yeah, we got to be very careful about this. I'm gonna be a stickler.
No, change into.
Okay, good. Displacement displacement divided by time, or elapsed time. Time's fine, we know what we mean, right? Okay, displacement's important though, because the other way we could say that is change in position, right? But what we can't say is something like distance, right? It has to be a vector quantity on top. So average velocity, and let's do it this way. That's the way I'm gonna do it on, I was making up a Moodle problem set, and in solutions I did that, so we're just gonna do it that way. So we know it's a vector quantity, the bar over the top means it's an average, right?
Okay.
Okay, so average velocity equals,
D with little hat.
good, delta D, and that's gotta be a vector D, right, for displacement, over
Delta T.
delta T, very good, okay? What else? Another vector quantity. Position, sure, position. What's our vector for that? Or, yeah, what's our symbol for that?
I don't know.
In this book, kind of a weird one, but,
It's a little. D with hat. Oh, that's it.
right? Okay. Now, does everybody see that that's different than displacement, right?
Yeah.
Displacement is the change between the final position and the initial position, right?
This is one position.
Right, and if it's initial position, we would put a sub-zero there. It's final position in our book, they put a 1 there, right? So that's what we'll do. What else?
Force.
Okay, force we talked about, good, and we'll get there, but force gets a little more complicated. Force involves some other stuff that we're not gonna discuss right now, so we'll get there. But in terms of just strictly motion, force isn't really there. Acceleration. And I guess displacement, right? So we left off with acceleration, and do you remember, without looking, what's the formula for acceleration? It's a vector quantity.
That's confusing though because velocity includes time. So
You're right, okay,
But the
you're
time
right.
is-
Velocity has time mixed into it, but velocity is a thing unto itself. So it is change in velocity over change in time. Now, if we wanted to,
Can you put an example of acceleration?
yeah, we're gonna do some right now, exactly. So before we jump into acceleration, let's just talk about these kinematic quantities for a second. Let's limit ourselves, how about to the vector quantities, although we could just as easily talk about their scalar analogs. So let's focus on time we won't worry about, but let's focus on the physical kinematic quantities we've discussed. So we've got position, velocity, and acceleration, right? Okay. Can you sense any of those?
Yes. No. No. Good question.
Well, let's just, I'm gonna do an experiment. Let's just see. What if did I do this yesterday?
No.
I didn't try this. Okay, we'll try it today. If I close my eyes, okay, does that feel any different than? No, it doesn't feel any different at all. I can't sense where I am based on, right? If somebody blindfolded me and led me in here, I would have no idea where I was if I didn't have some other clues, right? So that one we can check off. Doesn't work. Velocity. Okay, let's do a little thought experiment here. I want you just to imagine this. Imagine that you're in your car, taking a nap. You've got your hat pulled over your eyes so you can't see anything. The engine is just purring away. Does it make you want to take a nap right now? Just purring away. It's nice and warm. Can you tell what your velocity is? No. What it could be zero. You could be idling at rest. You could be cruising down the freeway. You have no way of knowing, right? Other than the engine speed, but let's pretend that doesn't count. It's a quiet car, right? So you can't tell velocity either. What about acceleration? Yeah, you can. You can tell that, can't you? That's the one thing you can sense is acceleration. You know that when you speed up, it's a definite sensation, isn't it, right? If you jump off of a high dive into the pool, you can sense the acceleration, right? I mean, it definitely feels different than it did when you were standing on the diving board, right? Okay. So this is the one that we're sensitive to, all right? So what about acceleration is change in velocity over change in time. So let's calculate some accelerations. How about? Let's start easy. Let's say, okay, hey, pay attention. Don't get, you guys are letting yourselves get distracted. Don't do that. You got to get this down here. So let's say when I cross the starting line here, that's when we're going to start our stopwatch. When I cross the starting line, I'm just at rest. I'm starting at the starting line at rest. We click the stopwatch, and I start to accelerate. And let's say I accelerate uniformly, okay? So at a constant rate. When I get out to here, it's taken me 2 seconds to get here, and when I get here, I'm going 6 meters per second. So what is my acceleration?
3.
3 what? You're right, 3 units of acceleration. What's that going to be?
7%.
Good.
Wait, now I'm confused.
So acceleration, my average acceleration is going to be constant in this case anyway, equals change in velocity over change in time. So let's calculate that. Change in velocity always means final value minus initial value, right? Whenever we talk about a change, it's always the final value minus the starting value. So my final value we said was 6, right? 6 meters per second divided by 2 seconds gives me 6 over 2 is
3.
so the numerical part is 3, and this is the other weird part. I think we had just barely talked about this, right? Meters per second squared. Did we mention that yesterday? No, we didn't. Okay, so this is a little strange. So we get meters per second. Now, what do we do? If we divide, we could make this seconds over 1 on the bottom. If we divide by a fraction, what do we do?
Times.
Well, flip and multiply, right? So this is the same thing then as saying 3 meters per second times 1 over seconds. So we write that as meters per second squared. Strange units, but those are the standard units of acceleration, meters per second squared. Okay?
What are you saying? Like I just accelerated 3 meters per second?
So the way we interpret this then, we interpret this, and we're going to talk more about this as we get into, like, here's kind of our immediate future looks like this. We're done with chapter 3 essentially. We've got some assignments for you to do, really lightweight stuff, kind of a warm up prior to roundup. We'll come back, we'll talk about how do we deal with vectors, because you can tell vectors are a big deal for us, right? These are vector quantities. So we have to kind of look at the math of vectors before we jump into any more physics. And that's sort of what chapter 4 does. And then in chapter 5, we jump into kinematics that's a little more empowered. Now we know how to deal with vectors, we can look at a little more complicated problems. And at that point, we're going to come back and revisit these quantities, and we're going to talk about them as rates. Okay? I mean, we can mention it now, but we'll talk in more detail later. Another way of saying this, acceleration is the change in velocity over the change in time. We could call that the rate of change of velocity. Anytime we're talking about the amount that a quantity is changing over an interval of time, if we're measuring the change with respect to time, we call that a rate, right? So one way to think about this then, the acceleration, the rate of change of velocity is 3 meters per second per second.
So every per second, you're moving 3 meters.
Right, so every second we're increasing our velocity by how much? 3 meters per second, right? Make sense?
Yes.
Okay. All right, so let's do another one. This time, let's say I'm start my stopwatch. I'm trucking along at 6 meters per second. That's really not very fast, but I'm going along 6 meters per second. And 2 seconds later, I'm at rest. Okay, so what's my acceleration there?
Negative 6 meters times.
Okay, it's -3, right? Because if we do the math this time, we'll just leave the same. I'll do it this way, how about?
But wouldn't you slowly?
Okay, so example 2, we would have gotten our final velocity is 0, right? So we get 0 minus 6 meters per second. And really that was a 6 minus 0, wasn't it? Divided by 2 seconds equals -6 over 2 is -3 meters per second squared. Okay, now I want you to, you have to reconcile this. Okay, this is something I want you to come to a point where this makes, you kind of say, okay, I got that. I know why that's negative. Can somebody articulate that? If I'm moving along in this direction.
You're slowing down.
Okay, because I'm slowing down maybe, right?
Yeah.
Agreed?
Yeah.
Okay, hold that thought. Let's do another example. Okay? Now, this time, I'm going to be going in this direction. Okay, same situation. I'm moving along from right to left, going, my speed is 6 meters per second. I'm gonna come to a halt in 2 seconds. What's my acceleration?
0.
No. One more time. Here's the picture. I'm running in this direction. That's important, right? I'm on a line. I'm on the x-axis. 6 meters per second is my speed. 2 seconds later, I screech to a halt. Okay, I'm hearing -3 and 3. Should we just put it in and see? Let's just see what the math gods tell us. They'll tell us the right answer.
You can't do it in my head.
Okay, so if we plug this in, delta V over delta T. So delta V is change in velocity. Now, what's my initial velocity in this case?
6.
Careful.
No.
How come? I'm going in this I'm going in the negative direction, so my initial velocity is -6, right?
Oh, okay.
Okay, my final velocity is, because I'm at rest, right? So then the math tells me that I get my final velocity minus -6 meters per second divided by 2 seconds. So what's my outcome?
3.
Yeah, +6. So I get 3 meters per second squared. But how can that be? Delaney suggested that in the last example, the reason the acceleration was negative is because I was slowing down. And in that instance, it was. But I guess maybe we can't say in general that slowing down means negative acceleration, can we?
But you're going to reverse.
Opposite the velocity.
Okay, good. So you want to articulate that. So if I'm slowing down, then the acceleration is, how do we know if it's positive or negative? Okay, because it's going to be in the opposite direction of the initial velocity then, does that make sense? Sure. So if I'm trying to get how I can draw that picture. Well, there's one picture I can draw. One picture that will definitely help. So but before I draw the picture, I want to say one more thing here. Let's just make sure we get this. So listen carefully. Now, this was weird, right? I'm slowing down, but my acceleration was positive. But I'm slowing down in the negative direction, right? So if I'm slowing down in the negative direction, would you agree that after I'm initially going -6 meters per second, right? The negative means in that direction. 1 second later, I'm going how fast? -3. Then I'm going, well, after one more second, I'm going 0. If I continued that trend, what would I be doing next? Going that way at 3, going that way at 6, right?
Why?
How come? How much is my velocity changing every second if I'm going from -6 to -3, -3 to 0?
Fast.
Isn't it changing by what? +3, right? So does that make, that's my acceleration, then it has to be positive, right? Because my acceleration, my velocity is changing in a positive direction. It's getting more positive, right? -3 is more positive than -6, agreed? I've added 3 to it, okay? So there's a little trick you can do here, and this does involve force. We're going to find out later, and we'll get into this in more detail, we're going to find out that force is always proportional to acceleration, right? So if I want to accelerate in this direction, I have to apply a force in that direction. That's pretty intuitive, isn't it? So imagine a little invisible hand that is going to push on you to cause the acceleration, and the direction of the push will tell you the sign of the acceleration. Make sense? That's helpful. So if I'm going in this direction, if I'm going in a negative direction to slow down, doesn't the hand have to push me this way? That's positive, right? Okay, make sense? Okay, what if I'm going, let's mix this up even again here. So let's say that I'm starting off at rest, and I'm going in this direction. After 2 seconds, I'm going 6 meters per second. So would you agree the magnitude of that acceleration is going to be 3, isn't it?
Yeah.
What's the sign going to be? In which direction is the hand pushing me? Negative, right? Okay, make sense?
Yeah.
Okay. So I don't know if I need the picture anymore, do I?
Well, yeah, you know it's
Because a picture here would be kind of hard to draw, except if I did this. Except this is the one thing I can see at this point. that might be helpful. We'll revisit this in chapter 5, and we're going to actually draw motion diagrams that'll make it a lot clearer. But we don't quite have that yet. We'll get there soon. But for now, we can say this. If we take the situation where, say I'm going in this direction and slowing down, then if this is the point that represents me, would you agree that the velocity vector, my velocity vector, is in that direction? Now, I have to add something here that we haven't previously really focused on. We've talked about average velocity, right?
Yes.
Now, imagine what instantaneous velocity might be like. Okay, and you have to kind of think about this. Imagine that I have a vector pointing out of my chest. That's my velocity vector, right? As I'm moving along pretty fast at 6 meters per second, that vector is long, pointing in that direction, right? Has a big magnitude. As I start to slow down, what's going to happen to that velocity vector? It's going to get smaller. I'm still moving in that direction though, right? So it still points in that direction, but it just shrinks. And when I get to 0, it's gone, right? Agreed? So interpret or visualize an instantaneous velocity as meaning kind of being represented by that vector. So when I'm moving in this direction, this might be my instantaneous velocity vector. In what direction am I accelerating if this vector is getting smaller? So this is V. The V is in this direction, but I'm slowing down, it's got to be out here, doesn't it?
Yeah.
Make sense? Right? Because my velocity is changing in this direction if this arrow is shrinking.
Okay.
Think invisible hand. Invisible hand is pushing on me in that direction to slow me down, right? Make sense? So because those vectors are opposed, their signs have to be opposite.
So then your acceleration is positive.
Right, so if my velocity is negative, the acceleration is positive, right?
But then on the one before that, velocity.
The one before that, I think I was slowing down in this direction,
Yeah.
right? So now if my velocity is in this direction, my velocity is positive, right? But if my velocity is getting smaller in that direction, that's equivalent to getting bigger in that direction, right?
Your
Same,
acceleration
agreed?
is less.
So it would be the opposite then, wouldn't it? It would be like this. I've got there's me, here's my velocity vector, and my acceleration vector must be in the opposite way because my velocity is changing in that direction, right? The arrow is shrinking, right? So it's shrinking in this direction is the same as growing in that direction, right? Kind of a weird concept, but that's how we describe motion. Okay? Questions? I think you guys are ready to go on this. I think you're ready to try this. I've almost got this first problem set done. The ones in the book, why don't we just work in here for a little bit? I'll let you guys work together on the book questions. The Moodle questions are getting pretty close. Those are going to be questions that are going to be more kind of numerical, where I'm going to tell you something like here's an example of one.